So today we are going to talk about diffusion models. Okay. Again, diffusion models are generative models. So we already talked about variational autoencoders. We talked about generative adversarial networks or GANs. We talked about normalizing flows. And diffusion models have, roughly speaking, a similar problem formulation. What is that problem formulation? We are given a training set, starting with the simplest case, and later on I'll talk about more sophisticated generative models where you can have additional inputs rather than input images. Okay, so you have a training set with n images, and we assume these images, they come from a distribution, an underlying distribution that we don't know. Let's call that distribution Q data of X. And our goal is to learn a generative model, P theta of X, such that P theta of X in distribution is similar to the underlying data distribution. So we are able to generate realistic samples. So that this assumption ensures the samples that we generate is realistic. Plus, we want to be able to easily generate samples from P theta of X. Easy generation. Okay, so this is the same problem formulation we started when we were talking about variational autoencoders, generative adversarial networks, normalizing flows. And in these cases, what we formulated X as a function, let's say f theta of Z, where Z is your noise or latent variable. Oftentimes we generate Z according to a Gaussian distribution to ensure we have an easy generation, the second requirement that we have. So you generate a Gaussian distribution and then you pass it through your F sub theta. That's your generator in the case of GANs. This is called generator. In the case of GANs. In the case of VAEs, we call it decoder. And in the case of normalizing flows, these were flow functions. Composed on top of each other, or the flow model. Okay, so with this overview of what we have already covered, diffusion models are not different. Again, we want to learn a function from noise to real images in a way that the distribution of the output matches the underlying distribution of real images, even though we are not aware of that distribution. The setup, the goal is the same. The only difference here is that this function is going to be a bit more complicated compared to the case of GANs or VAEs or normalizing flows. Okay? So that's the only difference that we have in diffusion models. Diffusion models use a different function f theta in their generation. And you're going to see this function f theta is going to involve adding and removing noise from images. Adding and removing noise from images. This is going to be the set of functions that we are going to consider. Functions that will add and remove noise recursively, and we are going to see how that function can, in fact, generate realistic samples. But from a high level, it is the same formulation that we have for diffusion models to GANs, VAEs, normalizing tools. And you are going to see, in fact, the way that we are going to develop this function is going to be extremely similar to the way that we started to think about the problem when we were talking about VAEs and GANs and normalizing tools. So that's the context. All right, so in diffusion models, as I mentioned, this family of functions that we have here involves adding and removing noise from images. So the way that it works, let's say during the training, you have some original images, some realistic images. Let's call this original image. One sample from your data set. Let's say it's an image of a tree. And this sample comes from a distribution, right? As I mentioned, this distribution is called Q data. So the problem is that we don't know this underlying distribution, right? That's the whole issue that we are trying to deal with when we are talking about generative models. So we don't know, this is unknown. So in the diffusion process, we are recursively going to add noise to the samples that we have in our training. That's called forward process. And you're going to see why that will become useful in the generation process itself. So we add noise recursively. So here you have your tree, but maybe with some noise on top of it. Okay, so you add more noise or add noise to the noisy version. So you get a noisier version of your image. And you do it until basically you destroy whatever information you have in your original sample. And then you add more and more noise that the resulting image is basically a noise image. You don't really see your original content in that image. Okay, so let's give names to each part. Okay. So here I'm showing one sample from your training. And I'm assuming that sample is coming from your distribution. So there's a distribution of your training samples. These are noiseless samples. These are original samples that you have. And that distribution is called Q theta. Or I'm going to refer to this distribution with the QX0. X0, it means your original noiseless distribution. Okay. When you are adding noise, let's say in one step, every sample will become noisier version of that sample at the previous time. So you're basically changing the whole distribution. So at this step, you're going to get the distribution QX1. So every sample is a little bit noisier. Okay, so similarly, at the next step, you're going to get qx2 up until the last step. If you're doing it capital T times, you're going to get qxt. That's the distribution of your samples, the noisy samples, after T steps of adding noise to your original samples. So that's the notation that we are going to use. Okay. Just to make sure that we are all on the same page, do I have a good characterization of qx1? And you can imagine the noise that I'm going to add for now is Gaussian noise. At each step, you're going to add a little bit of Gaussian noise or whatever noise that you want to add. Okay. If I know the distribution of the noise that I'm adding to my inputs, do I have a good characterization of qx1? Okay, so let's take a poll. Who thinks we have a good characterization of qx1 if I have a good model for my noise? Can you raise your hand? Okay, who thinks we don't have a good characterization of qx1? I would say 10% yes, 15% no, and the rest are either undecided or asleep. Okay, so we'll have to deal with that. Okay. Okay. So here's the thing, right? So I don't have a good characterization of qx0, which is my true data, because if I had it, then what I'm doing here, right? So I would just use that in order to generate more samples. I have a conditional distribution between x1 and x0. That's the noise that I'm adding. But since I don't know what my original distribution qx0 is, then I don't have a good characterization, mathematical characterization of qx1. Same for qx2, so on and so forth. Okay. So this process is called forward process. So one way to remember, obviously, when I'm saying forward process, you can immediately think that we'll have a backward or reverse process. So one trick to remember which way is forward, which way is backward or reverse. Forward, you go towards noise. So here, that's how we define the forward process. Okay, so at each step of forward process, we are adding a tiny bit of noise to or distribution from the previous step. Each forward step, a small added to inputs. Great. So here you have some flexibility. What is the noise model that you want to add? Obviously, we always start with the easiest noise model possible, which is Gaussian. So we are going to assume Q, the distribution of samples at time t. By time, I mean the steps that you are adding noise to your input. This can be thought about time 0. This can be thought about time 1. So these are the number of steps that you're adding noise to your inputs. That's the notion of time. The distribution of xt given the previous time, xt minus 1, we are going to assume it comes from a Gaussian distribution. As simple. The mean is going to be a function of your previous sample, xt minus 1, but a scaled version of it with some number, 1 minus beta t, and the variance would be beta t times identity variance, identity covariance. So this is a fancy way, maybe not so fancy way, of writing xt is equal to 1 minus beta t times xt minus 1 plus square root of beta t times a noise, where the noise comes from a normal distribution. Right, so you take whatever sample that you have in step t minus 1, scale it down a little bit, and then add noise to it. Why this model? You can use other models. This is one way of thinking about it. That's what I'm emphasizing. Right? So it is not like the only model that you have to use in order to have your diffusion model work. This is one way of thinking about it. So why these two coefficients? So when you do this, so when you are adding noise, you're adding variance to your data. So you scale down your data a little bit so that when you're adding noise to it, it doesn't blow up after many runs. So imagine if you're just adding noise and noise and noise to your data, eventually the norm or the variance of your data samples can be huge at larger steps. It ensures to have some preservation of your variance across different times. Okay. And I hope you understand this part, right? So when I'm multiplying my normal Gaussian with the square root of a number, the variance of the noise is the square of that number. Like if you have alpha times some noise, and noise is distributed according to normal, the variance of this is alpha squared. That is why here you see beta, and here you see square root of beta. So you are multiplying your noise with the square root of beta. The variance of the noise is beta. Okay. That's a forward process. Take an image, really easy, right? Assuming all betas are fixed. Some numbers, maybe a fixed number, maybe you can change these numbers for different t's, doesn't really matter, but they're constants for now. You scale down your input a little bit, add a little bit of noise, go to the next step. Scale down your sample at the next step a little bit, add noise, go to the next step, so on and so forth. So if I have an input at time 0, again, time means a step. There's like literally no notion of time here. If I have an input at time 0, which means noiseless, clean input that I have, in order to generate a noisy version of it at time 100, how many times I need to do this process? Roughly speaking. Roughly speaking, you're saying 100 times, so plus minus 1 or 2. Is it possible that I directly generate the noisy version, a noisy version of my input at time 100 without going through like generation at time 1, 2, 3, 4, so on and so forth? Okay, so let's see if that is possible. As I mentioned, xt is related to xt minus 1 via this equation. There is randomness in it. It is not deterministic. Right? So for each step that you're going forward, you're generating a noise vector and you're adding a scaled version of your input. So it is not deterministic where you are going to end up to. Even if you start with a single point, the next step you have a Gaussian distribution. And then each point in that Gaussian distribution can go to another Gaussian distribution for themselves. Okay, let's see what happens. Let's say I start with some point. My x1 is what? A scaled down version of x0, and I generate a noise let's say epsilon 0 according to a normal distribution, I generate x1. To generate x2, I'm going to scale down x1 a little bit and add some noise to it. Again, this noise is going to be regenerated. This is not the same noise vector I generated in the previous version. Every time I'm drawing a sample from my normal distribution. But can I combine these two equations? Because I have an equation for x1, right, from the previous slide. So if I do that, I can write this as 1 minus beta 2. Now, instead of x1, I'm going to replace the previous equation, which is 1 minus beta 1 x0 plus, okay, so what else I have? 1 minus beta 2, this multiplied by this term, which is square root of beta 1 times epsilon 0 plus beta 2 epsilon 1. So all I did was to replace x1 with this equation that I have. Okay, so what do I have here? Let's make some definitions to simplify notation. I'm going to define 1 minus betas as alphas. 1 minus beta 1, I'm going to call it alpha 1. And I'm going to define a combined alpha. So it's a combined alpha as 1 minus beta 1 times 1 minus beta 2, which means alpha 1 times alpha 2. Alpha 2 bar, it means I'm just multiplying alphas up until that point. Just a definition for simplifying my notation, nothing really fundamental here. So again, let's recall the notations. 1 minus betas, I'm going to individually call them alphas. And alpha bar is the combined alphas up until that particular time by multiplication of the previous alphas. Okay, therefore, the first term, I can write it as what? Square root of alpha 1 times alpha 2, which is alpha 2 bar times x0. Okay, what about the second term? What about this guy? Remember, epsilon 0 or E0 and E1, they are normal random variables. They're samples that I'm drawing from each from a normal distribution independently. They're not the same, but their distributions are similar. So what would be the distribution of this term? You have a scaled version of epsilon 0 and a scaled version of epsilon 1, and you are adding up these two random variables. What would be the distribution of the overall term? Fantastic. Let's look at it's a Gaussian, right? You know, a scaled version of a Gaussian is Gaussian. Sum of two Gaussians are Gaussian. So this is going to be a Gaussian distribution. Good. So what is the mean of this distribution? 0. Mean is 0, because the mean of epsilon 0 is 0. Mean of epsilon 1 is 0. The mean is going to be 0. Okay, what about the variance? Variance will be the sum of the variance of the first term and the second term. But previously I mentioned when you multiply a number to a Gaussian, the variance is the square of it. So the first part, the variance will be what? Perfect. 1 minus beta 2 times beta 1 times identity. And the second variance would be beta 2, right? times identity. Okay, can I simplify this term? Look at this term. Let me open this up. This is beta 1 plus beta 2 minus beta 1, beta 2. How can I simplify this term? I want to write everything in terms of alphas. Let's see. If I add plus 1 minus 1 to it, do you agree that this is equal to this term? If you don't agree, you can double check it. Okay, so what is 1 minus beta 1? Alpha 1. What is 1 minus beta 2? Alpha 2. What is alpha 1 times alpha 2? Alpha 2 bar, right? Perfect. So therefore, my Gaussian has 0 mean and alpha 2 bar times identity. That's the combined noise that you're adding. And if you want to write it in terms of the equation that we have, x2 is equal to the square root of alpha 2 bar plus the square root of, okay, so this should be 1 minus, apologies. Square root of 1 minus alpha 2 bar times a noise that is distributed according to a normal distribution. So basically, the whole point is that I can get the distribution of any time, let's say x2, without really going through like the middle distributions. I don't have to like add noise to x0, get x1, and then x2, right? Because the noise distributions that I'm adding, they're pretty nice, right? They're Gaussian noise, and addition of like multiple Gaussian noise, they're Gaussian noise. So you can just massage it and get the distribution of the whole overall noise that you're adding from time 0 to time whatever t that you're considering. So you can jump to any step in your forward process. So if you have sample from time 0, and I ask you, okay, in your forward process, generate a sample at time 10. You can say that is very easy because I have alpha 10 bar. It's constant. It's a multiplication of alpha 1 to alpha 10. And I'll multiply that with my x0. And then I draw a noise from normal distribution and I'll scale it with square root of 1 minus alpha 10 bar. And I'll just add it to my scaled down version of the input. There you go. You generate a noisy sample at time 10. So in general, at time t, you can generate your samples by combining a scaled down version of x0 plus 1 minus of that times noise, and noise is distributed according to normal. Just to be complete here, what is alpha t? It is multiplication of alpha 1 to alpha t. And what are each alphas? It is 1 minus beta 1 to 1 minus beta t. It's your forward process. So you may be asking, what are you talking about? You are taking some inputs and you are just adding noise to it. So what? You can add noise to your inputs. Like, who cares about it? So hold on that thought. You're going to see why it becomes useful. Okay, so let's look at these combined alphas. So alpha I, what is the range of each alpha? Can an alpha I be like 1,000 or negative or? Yeah, because we are assuming betas are a number between 0 and 1. That's the scaling down version of your input. You don't multiply your input with a negative number or with like a number bigger than 1. Therefore, each alpha is going to be a number between 0 and 1. Okay, so here you're multiplying t numbers between 0 and 1. Obviously, you can have like different quote-unquote scheduling, meaning that different constants for each alphas or each betas. That's a minor technical detail. But let's assume all of them are fixed and all of them are 1/2. How about that? So after, let's say, step 1,000, let's say assume for now, each alpha I is 1/2. That's my scheduling, right? How about that? So after 1,000 rounds, what would be the coefficient that you multiply to your x0? So it will be what? What would be the alpha 1,000 bar? It will be the multiplication of all of the alphas, right? So you have, let's say, 1/2 for each of them. So it will be 1/2 to the power 1,000. Therefore, your xt is going to x 1,000 is going to be what? Square root of it, which will be 1/2 to the power 500 times x0 plus 1 minus of this times n noise. Okay, can someone tell me, roughly speaking, what is the value of this? 1 basically to the 2 to the power of 500. Like literally 0, right? So at step 1,000, basically you only get noise, because the first term, roughly speaking, goes away. That's why I mentioned you're adding more and more noise until the content is completely destroyed. So alpha t bar goes to 0 as t goes to infinity. Therefore, distribution of xt given x0, that's the distribution at the larger time. This approaches a normal distribution. At step 1,000, doesn't really matter what was your original distribution. You could have had realistic images, you could have had whatever inputs. Really doesn't matter. You're just adding noise to it. Right? At step 1,000, you are going to always get, roughly speaking, a normal distribution. Make sense? Oh. Let me pause and see if there are any questions before I move forward. All right. If not, let's see why we are adding noise to the input. So what is the purpose? Again, let's start with the example that we started with. I have x0 if you notice, I abandoned my cat drawing. I realized trees are much easier to draw. So, okay, so we go to X1, add a little bit of noise to it. And at step T, XT, you get a noisy version. Right, so corresponding to it is Q0, Q1, QT. Okay, so let me make space a little bit. Let's look at time t minus 1 and also time t in the middle. Okay. All right. So this part becomes very important, so pay attention. Again, let me ask the question that I started the lecture with. Do I have Q0? No. Do I have Q1? Do I have QT minus 1? No. Do I have Q capital T? Yes, exactly. Because we added noise, more and more and more and more noise to it, it more or less converged to a Gaussian distribution. Okay, not a bad start, right? So at least we have a defined distribution at the end. Okay, so not bad. I don't have individual Qs. That's a bummer, but I have something at the very end. So what else do I have? So if I have Qt minus 1, I don't have it. Would I be able to get Qt? If I have the distribution at time t minus 1, would I be able to get the distribution at time t? Yeah, like that's a forward process, right? That's like adding noise to it. So the distribution, another distribution, I have a good formulation from xt given xt minus 1 is what? It is just a Gaussian distribution with some scaled down version of xt minus 1, and the variance is covariance is beta t times identity. But I have this distribution. It's a forward distribution. Okay. So I don't have this distribution. I don't have Q1. I don't have Qt minus 1. But starting with my samples, I can generate samples from Q1 because I know how to add noise. I know how to generate that conditional distribution and move forward up until I reach to my last point, Qt. Can I come back? If I have the distribution, again, I'm assuming I don't have it. If I have the distribution at time t, can I generate the distribution at time t minus 1? Okay, so again, the question is, if I have distribution qxt, can I generate distribution at time t minus 1? That's the question that I have. So I heard some yeses, but before going to see whether or not we can do it, suppose we can do it. But suppose if you have distribution t, qxt, you can generate samples from xt minus 1. This is called reverse process. I'm not saying yes or no or not, but suppose the answer is yes. Would that give me a generative process if the answer was yes? How come?
Because it's recursive, you can go all the way from the state of random noise all the way back to the image.
Fantastic, right? Because I know the last distribution, Q capital T, is roughly speaking a Gaussian distribution. That is the only marginal distribution I know. I don't know Q0, I don't know Q1, I don't know Q2, I don't know Q900, I know Q1000. That is normal. That is Gaussian distribution. But if I have a process that can reverse time, if you give me Q at time 100, I can generate Q at time 99. I can start from the end because I know Q1000. Q1000. That is just Gaussian. If I knew this process, I'm not promising you guys anything at this point. If I knew, I could generate Q999. And recursively, I could generate Q998. X, I mean like, okay, actually, we are just using that notation. Q999 up until Q0. And there you go. You hit Q0, you have the distribution of your original data. Seems too good to be true, right? What are we doing? We're just adding noise. We reach to a wall of Gaussian noise, and then I'm telling you, if I could reverse the process just one step, then I can go back to my original distribution that wasn't. This should give you a very strong clue that perhaps I can do this. Because otherwise, it would be too simple. All right, so let's see what is the issue. Right? So how can I go back from time t to time t minus 1? What is the obstacle that doesn't allow me to go back in time? So my goal, okay, now my goal is simple, right? Before I have a goal of, okay, you give me noise, I generate realistic, amazing scenes of dogs playing with cats next to ocean, whatsoever, right? But now I have simplified my goal. My goal is that you give me a distribution at time t. I just denoise it a little bit because that's how I generate samples at time t given time t minus 1. No, my goal is like just, okay, how can I denoise my sample just a tiny bit to get the distribution at the previous time? So what is the Q xt minus 1 given xt? The sub-goal, that's not the whole goal, because I know if I solve this, I'm done. I can start with Q1000, then I can go back and back and back in order to generate my samples eventually. Now, I basically broke down my overall goal to this really particular smaller goal that I can try to achieve. All right, so I need to compute this conditional distribution. What is one rule to simplify conditional distributions? Bayes rule. Thank you. Okay, so let's just write Bayes rule and let's see if it is useful. Xt minus 1 given xt is equal to xt given xt minus 1. Fantastic. I know this term. What is qxt given xt minus 1? It's Gaussian noise. It's a noise that I'm adding to my data, right? So I'm very happy at this point. You know, there's one term in the Bayes rule, it's in my favor. Right, so I need to multiply it with q xt minus 1, and I divide it by q xt. I have this term. This is just a Gaussian with a mean 1 minus, with a mean, oh, okay. It's Gaussian, right? So, with a 1 minus beta times xt minus 1 and a variance of um, uh, beta times, you know, beta times identity. Okay, so in order to compute this, but I need these two other terms. Do I have them? Hold on, don't say no so quickly, my friend. Okay. What about I start from t1000? So this will be 1,000, q1000, right? I would have this guy, right? That's my nice Gaussian distribution, right? So I'm down like with two terms, three terms. I need. I know like two of them. But what about this guy? Do I know that guy? How do you know? Gaussian with what? What is the mean? Because for instead, let's say 1,000, this is just a normal distribution. And for this one, I exactly know the mean and the covariance. But what about this term? But if it is the same distribution, then it is just Gaussian noise all the way. Your Q999 is Gaussian. Your then Q998 is Gaussian, normal, up until your Q0. I don't have this, bummer. Only one here. So, all right. Maybe Bayes' rule wasn't good overall, right? So, no use. Okay. Then what? So what is this guy? So let's think about it, right? You have xt minus 1. These are some noisy versions of samples. Say there's a house. Oh my goodness. And I won't disappoint you guys, your favorite cat. Okay, so these are samples that I get at time t minus 1. Obviously, the noisy versions of my input samples. I have a good idea of my forward process. I can get these samples by just adding a tiny bit of more noise to them. So this will be a little bit more noisier version. But my goal is to go backward. I want to find the distribution of xt minus 1 given xt. What is it? What is this process? Just forget about probabilities for now. It's like denoising, right? So you want to like remove just a tiny bit of noise from your data. Just a tiny bit, not all the way, because you want to go to just the previous step. It's the denoising process. But I can directly, statistically, get this number from my distributions. So how should I think about this problem? Because at the end of the day, you want a generative model. So with the generative model, if you think about it, one way is to have a probabilistic model on how images have been generated. Remember, that's how we approached VAE. In the VAE lecture, we said, okay, I am God, thank you. The way that I'm going to generate any realistic image is that I'm going to first generate a Gaussian sample, and then I'm going to push it through a neural network, say G theta of that input, and perhaps add a little bit of Gaussian noise to it. And that's how I'm going to generate my samples. And we said, given that model, that probabilistic model of the world, we go ahead and find optimal parameters for that particular data set using what was the approach to get good set of parameters for that particular data set? Maximum likelihood. We said, like, I'm assuming that my data is generated from this particular process. In the VAE case, we said generate a Gaussian noise and then push it through like a network. And that network has parameters, and let's estimate the parameters of that network according to a maximum likelihood optimization. Let's do exactly the same thing. Okay, so instead of having this probability, I'm going to approximate this or model this. That's a better word. Model this using a parametric distribution, xt minus 1 given xt. And theta is my set of my parameters. So now I'm a new God. It's a new lecture, new day. And I claim here's how all realistic images are generated. You generate your Gaussian noise at time, let's say 1000. And then you denoise it, go back to time 999 using p theta x 999 given x 1000. You denoise it one step. Suppose theta is given. Again, you are at time 999. Again, go back one more time. Go back and back and back and back until you reach time 0. And that is your true distribution or an approximation of your true distribution, and generate a sample from that. You may argue, are you crazy? Why should you generate images like that? It is a model. That is it. That's how I'm modeling my generation process. You could have modeled it differently, and we did model it differently in VAE. You said, okay, generate Z, just push it through a network and add a Gaussian noise. In normalizing flow, we did another way of modeling the whole generation process. This is another function. This is another parametric function to generate images from noise. We don't do it one time. We do it gradually. Generate noise and gradually decrease the noise. And find parameters theta that is fit to your training samples according to a maximum likelihood optimization. But does it have to be exactly this model? Why just the previous step? Not necessarily, right? You go ahead and define there's nothing fundamental about this. It is just a modeling step. That's why what I'm emphasizing. You could have, for example, model it saying that, okay, my generation model generate xt minus 2 given previous 2 times. You could have other types of generation process. There is nothing fundamental about the assumption that we have. Obviously, this is simpler because it has a Markovian assumption, saying that you're just going one step back. And when you go one step back, you really don't care about the earlier samples. But really, there is nothing fundamental about the model. It's just a model. Okay. All right, so I'm going to model my probability generation with this guy. But I need to like be a little bit more specific, right? So what would be a good parametric model? Let's say no, it's at your discretion, right? So you are thinking about how images can potentially be generated via this process. We don't care about the finding a good set of parameters at this point. Forget about that. Suppose we can do it later. So what would be a good model? Let's say you have noisy samples at time t. What would be a good model? What would be a good distribution at time t minus 1? So you're just denoising a tiny, tiny bit. Yes? Another Gaussian, because Gaussian is simple, right? But do we have to use Gaussian? No, but since Gaussian is simple, I'll go with your suggestion. Okay, so we are going to model it with a Gaussian. Okay, so what would you like to have as the mean of this Gaussian? Let's say you have a sample, let's say this particular sample, xt, and then you want to generate a distribution of all xt minus 1 in a way that if you added the Gaussian distribution, you would have got xt, right? So that's the whole idea. So what would be the mean of that Gaussian for xt minus 1, given that particular sample xt? Yeah. It can be any function, right? And you can use a neural network for that function. So we are going to use a neural network that take input xt into account. So it takes xt, your sample at time t, and it generates the mean of the sample, a little bit of a less noisy sample at the previous time. Kind of reminds you of VAE, right? Because in VAE, we had like this Z and we generated a sample and then we added a little bit of a Gaussian. Here's the same thing. You take XT, you denoise it, and you add a little bit of a tiny Gaussian noise, which is equivalent to saying that my mean is a function of XT and I add a tiny bit of noise to it. Right? That's the process. You have like a little bit of a noisy sample, you push it through your network, you denoise it a little bit, and then you add a tiny bit of Gaussian noise to it. Another way of saying it, the distribution that you have is Gaussian with the mean of that function applied to your xt and that tiny bit of noise as your covariance. Okay, so this function that we have here, this guy, should it be a function of the step, the time, or not? Okay, so what is this function? You are saying that you get a distribution at time t, and you go back a little bit. Does it have to be a function of, okay, so obviously it has to be a function of the xt, but does it have to be a function of time or not? I would say not necessarily, right? So if you could have a general function that can somehow detect the noise level potentially at your input and get an idea about the time step, maybe you don't even need this. But in many cases, it is helpful to add the time as an additional input so that it helps your network to understand what time or what step it is at, so that the denoising is done according to that particular time. Okay, so the MUT, this network, has an input, which is an image, plus time, plus the step that the denoising is being done at that particular step. Yes?
Is the output of U to be like a single number, a single or?
It is an image. Because basically what it does, okay, so intuitively, let's think about it. Okay. So this guy, this mu, it takes one of the samples that you have, and it tries to recover back a little bit of a less noisy sample. It will have the same dimension as your original sample that you had as your input. Okay. For now, just imagine T is given as an input. Later on, I'll explain how it is implemented. That is less important in our formulation. Okay. That's it, right? So given this model, I claim you have a generative process. So what is the generation process? What is the distribution at time 0? If I give you theta, suppose I tell you like exactly the weights of your function that is denoising your input, what would be the induced distribution at time 0, which is the distribution that you're generating your samples? So you start with distribution at time t, capital T. This is known, right? So this is just the normal distribution because you added like so much noise to it. And then you go one step back. You say, okay, so the conditional distribution at time t minus 1 given xt multiplied until conditional distribution at x0 given x1. In other words, you generate a sample at xt, that's your distribution, then you go back one step. That's exactly the process that we described. Go back one step, you have samples at step 999, go back and back and back and back to reach at time 0, and then that's your generation. That's it. That is called diffusion process. So you train your model, you learn a theta, a set of parameters for your denoiser. Many times it is called a denoiser. Obviously, now you understand why it is called a denoiser. And for the generation, you generate a sample from Gaussian noise with an assumption, let's say it is time 1000. And then you go back, you denoise it one step, two steps, up until step 0, and that's your generation. That's it. That's how state-of-the-art generative models for images, for videos, or even audio, other modalities are currently being developed. Okay, so the only remaining task is to learn this theta, right? Because that theta should be your data specific, right? So you can't have one generative model for everything. How to learn theta? What is theta? Theta is the parameter of your denoiser. So you have the sample at time t, you denoise it using this function. That's the mean, and then you add a tiny bit of Gaussian noise, which variance sigma square I, and that's your time step t minus 1, and you go back. So theta is the set of parameters that you need to learn. Okay, so how would you learn? What would be your approach? And please don't disappoint me, all of you. What would be the approach to learn theta from your data? Maximum likelihood, right? So again, this is the foundation. This is all you need to know. You assume there is a probability model for your world. Doesn't really matter what is the probability model. It's GANs, VAE, so on and so forth. Here we are using this recursive denoising as our probability model, as the way that we are generating samples. This probability model has a set of parameters, and you learn those set of parameters by finding the most likely parameters given your data set. That's it. That's the maximum likelihood approach. So we'll find theta with the maximum likelihood. What is maximum likelihood? Likelihood. Let's just write it down. I want to maximize the likelihood log of p theta of x0 given x0 comes from my real distribution, right? Q0 or Qx0. That's the notation we are using. It's a real data. I have samples from the real data. I'm going to compute the likelihood of each sample for a given theta, and I'm going to look at the average of those log likelihoods, which is the product of the probabilities, assuming that samples are generated independently, and find a good theta. That is it. You find a good theta, you can use it in your denoiser, and you have a generative process. So can we solve this optimization directly? So we did the similar approach for normalizing flows, if you remember from the last lecture. For normalizing flows, we had the probabilistic model. We wrote the likelihood function. Did we directly optimize the likelihood function? Yes or no? Yes. Thank you. One person was listening. That's all I needed. One person. So in normalizing flow, the amazing property was that I could exactly compute the likelihood. Remember, the likelihood was, the only term was like that Jacobian term that was problematic. Then we put some structure in the functions, in the modeling, to make that easier. And we exactly solved the maximum likelihood. What about VAE? Right? In VAE, again, we use a similar approach. We had a probabilistic model. We formulated the maximum likelihood. Could we solve the maximum likelihood directly? No. And what was the approach that we did in order to approximately solve the maximum likelihood? We used the variational lower bound. A variational lower bound is a lower bound on the likelihood function. So let's say it is your likelihood is here. Log p theta of x. We can't optimize this, but if I find the lower bound on the likelihood function, I maximize this lower bound as much as I can, then maybe the theta I'm going to find is a good solution. So you can check it. We are again in the same situation that we were using VAs. We cannot directly optimize this maximum likelihood optimization process. So we need to get a proxy for the likelihood function, a lower bound on the likelihood function, in order to solve this optimization. But it is very similar. The rest is like some technicality, right? So we are going to get the lower bound, maximize the lower. That's it. So this variational lower bound that I'm going to talk about has been addressed in many papers. You can look at the course webpage to see the details. So there was one paper in 2015 that computed the lower bound, Ho et al. 2020, they had a reformulation of it, and there are many relevant literature that you can find about how we can compute a lower bound on this. Okay. So let me look at. Thanks. Oh wow, really? Okay. Okay, so originally when I was going through the papers, I had skipped this one. So I did drive myself. It requires some algebraic manipulations, and you get an objective. And I was saying that, okay, you guys really don't have to see it, right? You don't have to see the ugliness of what we are doing. And then I realized that there are some terms that won't make sense if you don't see that ugliness behind the scene. So with that, I give you good news. Next lecture, I'm going to show you that ugliness of driving that variational lower bound, and you are going to get a little bit of a feeling of why we get some terms at the end of the day that by just looking at those terms, it may make less sense to you if you did not see those. Next, I'm going to compute a variational lower bound for the objective, the log likelihood objective that we have. In order to do that, let's look at this quantity. KL divergence between two distributions, Q distribution, my forward distribution, of x1 to t, it's a joint distribution of x1 to xt given x0, and the same distribution x1 to t induced by theta, by p sub theta given x0. All right, so if we look at the picture that we had in mind, okay, so here's my x0. I add noise to it, I get x1, I add noise to it, I add noise to it, I get xt. So the forward process is governed by Q, right? So Q, you can either think about it as a conditional distribution, that you have Qx0, then you get Qx1, because you have Qx1 given x0, so on and so forth. Or alternatively, you can look at the joint distribution of x1 to t given x0. Similarly, the reverse process is governed by distribution p sub theta. That's the distribution xt minus 1 given xt. You can, again, look at marginal distributions, or you can look at the joint distribution induced by p sub theta for x1 to xt given x0. So roughly speaking, what was my goal, right? So remember, I couldn't compute Q for the reverse process, right? So I couldn't compute Q xt minus 1 given xt. That was the reason I modeled that using P sub theta xt minus 1 given xt. So I'm hoping the induced distribution on x1 to t through Q and P sub theta, they should hopefully be close to each other, right? So that's my hope. That's why I'm quantifying the KL divergence between these two joint distributions. And because I don't want to like talk about individual marginals. If this whole joint distribution by Q and P sub theta, they're close enough to each other, maybe I'll be happy. All right, so let's write this down. Okay, so do you remember the KL, the definition of the KL divergence from the VAE lecture? What is the KL divergence between two distributions, let's say Q and P? Yeah, the simple formula using the expectation. It is the expectation over the first distribution Q log of the first distribution divided by the second distribution. Assuming these are, for example, densities. Okay, so that's the definition of the KL. Easy, right? Expectation over the first distribution, log of first distribution divided by the second distribution. Okay, so let's just write this down. Expectation over Q, okay, log of the first distribution divided by the second distribution. Log of the first distribution, which is Q, x1 to t given x0 divided by the second distribution, which is p sub t, x1 to t given x0. Just the definition of the KL divergence. All right. So next, I'm going to bring this x0 to the argument. And why I am doing this? Because at the end of the day, remember, my goal is to somehow model or get some sort of approximation for p theta of x0. So that is the goal here, right? So that is like my end goal. So I don't want this x0 to be here in conditioning for p sub theta. So I'm just trying to bring it to the main argument. Okay, so how can I do it? Bayes rule, right? So thank you. So this conditioning is equal to p sub theta of x. Now I bring 0 to my my argument, so it will be from x0 to t divided by p theta of x0. So all of a sudden you see the probability p theta of x0 appears in my bound. So that's good, because that's the quantity that I'm interested. I'm not interested in like, you know, p theta of x1 or p theta of x. Who cares in the intermediate steps? What is your induced probability? So what I care is this guy, p theta of x0, and all of a sudden it appears on my equation. Hold on a second. Okay, so let me simplify this. So here's the division, so I can bring it up to my numerator. So what do I get? I get expectation over Q log of p theta of x0. So this goes up times Q that I have, Q x1 to t given x0 divided by, now I have p theta of x0 given t, x0 from 0 to t. So I have this thing. Okay, so if you look at this equation, so I did nothing here fancy, so I just bring p theta of x0 to my numerator. So if you look at this term, p theta of x0, it doesn't depend on my q. So I can't bring it out of my expectation. So what I'm going to get is that actually it depends on q0. So let me just write it this way. Log of p theta of x0. Basically, I'll apply log function to the two terms plus expectation over q log of q x1 to t given x0 over p theta of x0 to t. So I broke down this log to these two terms. One term was this one, the other term is like these two terms. So therefore, if I look at the first part, expectation over q log of p theta of x0, I can just write it as the negative of this term minus of this term. Minus goes into the expectation into the log, and then basically I switch the denominator and the numerator, so I get the expectation over q log of, now I have in the numerator p theta of x0 to t over q of x1 to t given x0 minus of this term, and I have this KL term between q x1 to t x0 x1 to t given x0 and p sub theta x1 to t given x0. That's the KL term that we have on the right hand side. Okay, and if you notice, by q here, I mean q x1 to t given x0. Therefore, this x0 is not a function, in the expectation. So I can just drop this expectation altogether, because this is taking the expectation given x0 over x1 to xt. So my x0 is like a constant for this expectation. So therefore, what do I have? I have log of p theta of x0 is expectation over q log of p theta of x0 to t divided by q x1 to t given x0 plus this KL term that I'm not going to write. This is an exact likelihood computation. There is no approximation up until this point whatsoever. I just basically massaged my formula a little bit to write my log likelihood in this particular form. Now, I'm sure most of you or all of you expect what I'm going to do. Right? So I'm going to drop this KL term. So KL is a non-negative number. So if I drop this KL term, I get a lower bound on my log likelihood. And what is this lower bound? That's a variational lower bound. Log of p theta of x0 is always going to be greater or equal to expectation over q log of p theta x0 to t divided by q x1 to t given x0. That's it. That's a variational lower bound. Lower bound or elbow bound that I have. Evidence lower bound on my log likelihood function. Just simply massaging my log likelihood to get a KL term that is kind of troublesome for me and dropping that KL term. Again, a similar technique that we use for the VAE part. Okay, so let's just look at this equation. So in the VAE, if you remember, we had that Q distribution, which basically was the distribution that in latent space. And it made sense intuitively what we are optimizing in our variational lower bound. So what about here? So let's get a feeling about these terms. So instead of maximizing this, I'm going to maximize my lower bound, right? So I'm going to solve this maximization. So let's see why it makes sense. So the first term is P theta of x0 to xt. It's a joint distribution divided by conditional distribution of q over x1 to t given x0. Okay, so let me just have some hand wavy argument. So if we want to decompose this in this form, so how can I write it? It will be like p theta of x0. It's a joint distribution, right? So you have p theta of, when I write x0 to xt, it means x0, x1, x2 to xt, right? That's the notation. So how can I bring out one p theta of x0? Just the joint probability rule, right? So this term can be written as p theta of x0, p theta of x1 to xt given x0, right? That's the numerator, divided by q of x1 given xt given x0. Make sense? So in other words, the terms that appear here, they are comparable to each other. So one is like the induced distribution from q over time 1 to t given x0, and the other one is the induced distribution by p theta from over time 1 to t, x1 to t given x0. So that's basically the intuition that I hope you have. Okay, so we are maximizing this quantity. If you, again, in a very hand-wavy fashion, you can bring this q to your numerator, bring this p to the denominator, and minimize this, right? So adding a minus sign. So adding a minus sign, this will be minimizing over q over theta, expectation over q, this term, q x1 to t given x0 over p theta of x0 to t. Okay, so let's look at it. Expectation over a distribution, log of that distribution over log of another distribution. Does it remind you of something? It's like KL, right? But it is not actually KL. Because the support of these distributions, they don't match. So if you look at like this is px0 to xt, here you have like qx1 to xt. So it's a little bit more complicated than that, than just the simple KL. But you can get the intuition that we are, again, matching these two distributions from the forward process and from the reverse process to each other using our optimization. Okay, so here's the variational lower bound that we get. And next, again, this seems complicated, right? Because it has p theta of x0 to xt. It's a joint distribution from time 0 to time t. And the denominator has like x1 to xt. Again, another joint distribution with like one fewer time, but it has a conditional distribution. So next we are going to massage it in order to come up with an extremely simple objective for us to solve it via an optimization. But let me pause and see if there are questions up until this point. I think there was a question before. Maybe I'll start with you. Yes?
Can you explain how you remove the expectation over log of PTX. And you said
Oh, this one, this is the right. Okay, so what is Q here? It's a little bit of an abuse of notation for me. So Q is this distribution. It's a distribution of x1 to t given x0. That's the definition of KL, right? So KL of two distribution is expectation over the first distribution, log of that distribution over the second distribution. When you have this conditioning on x0, it means, it is x0 is like a constant. It is fixed for you, Q of x0. Therefore, this term doesn't really depend on the Q. It can come out, it's a constant number. So you're just like averaging a constant number over whatever distribution you want. No. It's just that it doesn't depend on the Q because of the definition. Yes.
Well, why isn't it exactly KL?
So which part?
The very last
part. Okay, so all right, so let's think about it. So what is Q? Q is a joint distribution over x1 to t, right? So it's a conditional distribution. Actually, the definition of the Q here is also, no, you're right. So it is actually KL because the definition of the Q is also a conditional distribution here. So it matches. So I thought that it's a joint distribution. So it's an expectation over Q of the first distribution divided by the second distribution. You are completed. Okay, any other questions? Yes? I should have started with you because you had your hand raised early.
So we dropped one term. I think we did the same thing when we were doing VAs as well. So how do we know that this upper bound is tight enough for it to generate sensible things, or is it just an empirical?
Absolutely, it is just empirical. We don't know. But that's a fantastic question, right? Because I'm just dropping a term that I hope it is small, but from in practical scenarios, when you're using like neural networks and complex distributions, it is just empirical. And you're going to see, in fact, like, we are going to even have further heuristic changes to the objective later on. But empirically, it works. It would be interesting. I think there are some works that they try to understand the tightness, maybe under some simpler setups. I think that could be even a good topic for a final project if you are still looking for some angle. Looking at this bouncing, whether or not this is tight under, what conditions for what distributions you get a good bounce. I think that could be an interesting final project. Okay, so let me carry on. Okay, so I have this objective and I want to simplify this. So I maximize this, or I can minimize a negative value of this objective. So I'm going to go with the minimization because at the end of the day, I wanna have a form of a loss function. The negative of that objective log of p theta x0 to t divided by q x1 to t given x0. Okay. Let's write this down because I really don't like joint distributions in this sense, right? Because when I'm talking about x0 to t, it means that this joint distribution of x0, x1, x2 to x2, it's like huge, right? In terms of the input to my distribution. So let's just break it down because I have a better control on the marginals. Let's say, what is the qx0 or qx1 or qx2, and also the conditional distributions. All right, so let's just simplify these joint distributions a little bit. So for the numerator, remember P is the modeling that I have for my reverse process. So it is easier to break down the joint distribution from the capital T to x0. But that's a more natural way of thinking about the distribution P. Okay, so we are going to do that. We start with the distribution at time t, and I drop theta for this distribution because at time t, I'm assuming I already converged to a normal distribution. So there's no dependence on theta. But the time before that, xt minus 1 given xt will depend on theta. That's the denoising part that I have. So these two will give me the joint distribution of xt minus 1 and t, capital T minus 1 and t. And I have like this Markovian process. So if I want to include one more in my joint distribution, I only need to include the conditional distribution to the next time step. So I'll just write this down up until time x0 given x1. So that is the breaking down of my numerator. All right, so what about the denominator? So for the q, it is more natural to start from x0 and go towards xt, right? That's the forward process. Okay, so let's do that. Let's write it down. But look at this part, right? So the numerator, I have joint distribution of x0 to t, but in my denominator, I have the distribution of x1 to t given x0, right? x0 is given. Therefore, the way that I'm going to break it down is that, okay, so let's start with the first term, which is x1 given x0. Basically, conditioning on x0 is going to be on all of my terms because my joint distribution is conditioned on x0. Then the next term will be distribution of x2 given x1 because of the Markovian property, but I still have x0 because of the conditioning on my x0. Up until the last term, which is qxt given xt minus 1, but I still have x0 here because I have a conditioning on x0. It's a simple probability, joint probability breaking, right? All good? Nothing fancy so far. I hope you feel comfortable. So what we did is that we massaged the log likelihood a little bit. We dropped the KL term. And now I'm just like playing with each term in my elbow bound or variational bound. That's it. Okay. All right. Let's rearrange these terms a little bit. So I have the minus expectation over Q. Okay, so I'm going to keep PXT here. And I'm going to have the last term, probability theta x0 given x1. For the rest, I'm going to just write as a product T2 from 2 to capital T, P sub theta of xt minus 1 given xt. That's basically, I have the first term here, I have the last term here, and the rest of the terms are covered in that product, just like combining. And for my denominator, I'm going to keep the first term, qx1 given x0 here. And for the last terms, I'm going to write this as a product from t to 2, q of xt given xt minus 1 and x0. Just writing the whole thing as a product. So log, when applied to the product, I can break it down. So I'm going to consider this as one term, and I'm going to consider the second part as another term. So I can write the whole thing as minus expectation over Q log of Pxt probability theta x0 given x1 Q x1 given x0 plus, now I have the product from T2 to capital T, and log applied to the product will turn that to summation. This will be sum from T2 to capital T, log of individual terms, which will be P theta xt minus 1 given xt divided by Q xt given xt minus 1 and x0. Does it make sense? I'm just putting them in groups and applied log. It broke down this multiplication. Okay, so I have the log of the first term, and then this product will turn into summation. Log goes into it, and I have one term which is probability theta xt minus 1 given xt divided by q xt given xt minus 1 xt. All right. So believe it or not, this is the moment. This is exactly why I am walking you through this ugliness of driving the bound, right? This is the part to look at these equations and see really what is going on. Okay, so let's ignore the first term for now. Here I have a distribution P theta that naturally runs from the capital T time capital T to time 0. So for the joint distribution, in order to characterize it, I start with like the last distribution, and then I go back one step at a time, and that's my joint distribution. But Q is the distribution that runs from time 0 to time T. And I'm basically trying to match these two distributions. Okay, so here I have time 0, x0, x1 to xt. So Q runs in this direction. Maybe I should add a couple of intermediate points. Xt minus 1, xt, xt plus 1 to x capital T. Q runs in this direction. It is natural to break down the joint distribution of Q from x0 to x1 given x0, so on and so forth. And P runs from this direction, P theta. And I want to match these two joint distributions. But that's the goal in my optimization. But naturally, I'm going to have some sort of index mismatch. Because, for example, if I look at like these points, the Q is what? Q xt given xt minus 1. Further, I have always a conditioning on x0 for the Q, for the forward process in my equation. And for P theta, I'm going to have xt minus 1 given xt. So here, that's why we have P theta xt minus 1 given xt. And in the denominator, I have Q xt given xt minus 1. So these are actually in like opposite directions. Because there is no other way, because one distribution is running forward, the other distribution is running backward. I'm forced to have terms like this. But additionally, I have this x0 as my condition for the Q distribution. And where does this come from? This comes from this original conditioning on x0. that's essential because we got x0 into the argument of p theta, and we took it out in order to have a lower bound for the log likelihood for x0 using p theta. So this conditioning is really essential. You cannot ignore it because the whole thing is really depending on that. Okay. So this is important, right? So that's why I have a mismatch between the indices in my p theta, xt minus 1 given x2, and qxt given xt minus 1. Additionally, I have this x0 here. Okay. But I don't like it, right? Because when I'm comparing two distributions, I want, like, I wish I had here something like q xt minus 1 given xt, like q in the reverse direction, to be able to compare it with the p, or the other way around. But let's say I'm doing it with q. So how can I do it? How can I change the order here to have at least the indices of t and t minus 1 to match the indices that I have in the numerator? I can use another Bayes rule. So let's see what happens. Right, so Bayes rule, when I use over xt given xt minus 1, remember there is always an x0 here. That's the conditioning. So it is, you can imagine x0, the conditioning remains in all terms, and then use the Bayes rule on the rest. Hold on a second. So I have q. Okay, so 1 second. So I have q. Now I can reverse these two, xt minus 1 given xt. I still have the conditioning on x0 times q xt given x0 divided by q xt minus 1 given x0. It's the Bayes rule. Right? Now I'm going to replace this in my denominator. As simple as that, another Bayes rule. So let's see what we get. Okay. So this pxt is just a normal distribution, right? It doesn't depend on my theta. I'm just going to ignore it to further simplify my optimization. So the whole thing will be what? So I have the negative of expectation of q log of p theta of x0 given x1. That is the first term, divided by q of x1 given x0. Again, I can even like break down this log of p theta minus log of q, and given x0, I have a good understanding of this distribution, so let's not worry about that. Ignore this term for now. So the important term is the second term. Minus expectation over q, sum from t to capital T, log of, so log of what? So this guy divided by this guy, right? So I have this term, and instead of my denominator, I'm going to use this term. I'm going to use this term. So if you plug that in, so I can put this next to p theta xt minus 1 given xt, because the indices, they match. I have p theta xt minus 1 given xt over q xt minus 1 given xt and x0 times these two terms times q xt minus 1. Okay, maybe I'll just write it down here because I don't have space here, times q xt minus 1 given x0 divided by q xt given x0. So nothing fancy. I just replaced the base rule in my equation. Even better, I have log of the product, so I can apply log. So I have also log of this. So I have these terms. Okay. So let's look at the different terms that we get. Here, the first term, what is it? It is log of p theta x0 given x1. It is pretty manageable, right? Because p theta, remember, it is the distribution that gives me the distribution of one step back. It denoises a little bit. So I have a good understanding of this distribution, this conditional distribution. P theta runs naturally. So I'll just remind you the definition of P theta, which is just this Gaussian distribution with a mean mu theta of xt and t with some variance. So the first term now is pretty much manageable. Okay, so what about these terms? What is the distribution of q xt minus 1 given x0? What is it? Just a Gaussian distribution. Does it depend on theta? Just doesn't depend on theta. Assuming that betas and everything are fixed, right? Forget about it. What about the other distribution? Again, another Gaussian. Doesn't depend on theta. I don't care about it in my optimization. So I'm left with this term. P theta xt minus 1 given xt divided by q xt minus 1 given xt and x0. And this q is in the notation, it is a distribution from 1 to t given x0. So that's the notation that we have. So you can further massage this. I'm not going to do that because that's not going to give any additional intuition. To only have the expectation over your q x0, right? Instead of having the distribution over the joint condition on the x0. Okay. So I'm going to skip that. You can look at like the papers to do it. And you get a loss function in this form. So you're minimizing over theta. The first term is expectation over qx0 of KL divergence of q. Actually, I don't even need this term because that's constant. So everything is expectation over qx0. So the first term is minus log of p theta x0 given x1 plus p to 2 KL. So you can think about it, expectation of q log of, you bring this minus side inside q over p. So it is another KL of two distributions. One is q xt minus 1 given xt and x0 versus p theta of xt minus 1 and xt. plus some constants that I don't really care in my optimization. So in my optimization, I'm going to have some samples from my true distribution. The first term is minus log p theta x0 given x1, and I have t minus 1 terms that are KL between these two distributions, Q of xt minus 1 given xt and x0, and P sub t of xt minus 1 given xt. That is the objective. That's what we try to solve. And the rest are constant. So originally, I was actually just going to show you this. Right? And I was going to try to explain, maybe intuitively, what is really going on here. Okay. So let's see if we have a better understanding of what is going on. Okay, so let's look at one of these terms. So here you have two distributions, Q and P. Remember, the original intuition we had was to have a reverse distribution P when you're going from time xt to xt minus 1. So we can somehow approximate the conditional distribution qxt minus 1 given xt. Remember, that was basically the way that we started thinking about this. We were saying that, okay, look, if I could compute xt minus 1 given xt, I could have a generative distribution because I can start from the last time, go back one time ahead. I can get samples from the Q0. We couldn't do it. And we said, okay, what about I approximate the whole process with some other distribution, P sub theta, and let's use maximum likelihood. That was the intuition, right? So if you think about that intuition, you would maybe argue that, okay, maybe one loss function can be just look at the KL divergence between these two. Look at the KL divergence between P theta xt minus 1 and xt, and Q xt minus 1 and xt, and maybe sum it up over different times. That would be like a heuristic loss function that you could use in order to approximately model Q and P sub theta to be close to each other. Do we get that in our objective? So we get KL, that's good, a loss, a distance. We get the distance between two distributions, Q xt minus 1 and xt, given xt, P theta xt minus 1 and xt, exactly what we had an intuition initially, but we have a separate term here. There's an x0 here, conditioning on x0. And I was emphasizing that I cannot just drop it. It is not an artifact. I need to have it. So this term is a little bit more complicated, right? What it is saying is that, okay, so I want my reverse distribution, P theta of xt minus 1 given x0, given xt, my reverse distribution from time t to time t minus 1, to not just approximate my Q distribution, Q xt minus 1 given xt. It should approximate it knowing the original x0. Because maybe one intuition is that, and I'm again just adding some hand waving intuition, especially at later stages, you're basically having noise, right? You have added so much noise to your input. What does it mean to go back one step? You have noise, right? But if you have your conditioning on your original input, saying that, okay, look, yeah, this is a noisy image at time t, maybe there is no content in it, but my original image was x0. Then reverse process makes more sense because it is denoising in the direction of x0. If there is no direction, it may be hard to do the denoising because at the end, you just have like a pure noise. Okay, so what is the direction that you want to denoise to? So that is why we get intuitively, again, you know, it comes from the variation lower bound, right? So that's algebraic way of explaining it. But here's some hand-wavy intuitive explanation of why we have x0 here and we don't have x0 in the denominator. Okay, so that is the intuition, really important, x0 there. And the first term I'll mention how we usually have. So, okay, so let's look at the first distribution, p theta x0 given x1. So what is this distribution? It is a Gaussian distribution. So p theta, remember p theta is just a Gaussian distribution of mu sub t and some variance. So given x1, I have a distribution over x0. There are some usually some processes done on p theta x0 given x1 because your images, the pixel values are basically discrete, 0 to 255. But now we are having p theta x0 given x1 as a Gaussian distribution, which can have any value. So usually the way that it is being handled, it is a technicality, but you have a Gaussian distribution, you can just quantize it. And depending on what value that you get, you pick the right bin, the index of the right bin. And for the tails, you just map it to the last bin. It's basically just a quantization in order to be able to generate pixel values that are discrete, 0 to 255. And in fact, the way that it is handled, they usually scale it to the pixel values to have numbers between -1 and 1. So linearly scaling them. Okay, so that's basically the first term. What about like this term? So let's write this down to see if we can get an easier term to deal with that KL divergence. Okay. So the denominator is actually quite easy to handle. P theta xt minus 1 given xt, what is it? It is just the modeling that I have for my backward distribution, which is mu of xt minus xt and t with some fixed covariance. So the only problem I have is in the numerator that I need to work a little bit on it. So my numerator has q xt minus 1 given xt and x0. So I'm going to use another Bayes rule in order to be able to work with it. Again, I'll convert it back. Remember, we did convert it, the Q distribution to the reverse just to match it with the P. Now I'm going to do the other direction. So I'm going to write this as Q xt given xt minus 1 and x0 times Q xt minus 1 given x0 divided by Q xt given x0. Okay. So what is this distribution, Q xt given x0? Gaussian distribution, right? So I have it. In fact, I have a closed form. So that's the square root of alpha t bar x0. That's my mean. And my variance is this guy. So what is Q xt minus 1 given x0? Again, another Gaussian distribution. I know exactly the density of it. So what about this guy? What is the distribution of xt given xt minus 1 and x0? It's another Gaussian distribution with different mean and different covariance. Okay. So if you write this down, you get a Gaussian distribution with some mean and covariance. And if you do the algebraic computation, so you can basically look at the densities, overall, you can write this distribution as a Gaussian distribution with some mean. Let's call that mu hat theta of xt and x0, and some covariance that is a scale version of the identity covariance matrix. Okay. So we get also closed form formulas for these. So it is just algebraic. You just replace these coefficients, these densities, these coefficients. You work. It is actually quite a bit of massaging in order to get in the form of a Gaussian density, but you get another Gaussian density. This part is basically algebraic manipulation. Okay, so the terms that you get, mu hat of t, x0 and xt is in this form: 1 minus beta t xt minus beta t divided by 1 minus square root of alpha t bar times epsilon. What is epsilon? Epsilon is defined in this form because your xt, you can write it as alpha t bar x0 plus 1 minus alpha t bar epsilon. So here, instead of x0, I'm just going to replace it with epsilon. So that is the mean. And the variance is 1 minus alpha bar t minus 1 divided 1 minus alpha bar times beta t. Quite complicated, quite unintuitive, I would say. But you just replace the densities, you massage it, and you get the means and the covariance like this. Okay. So this again is going to be a Gaussian distribution with this mean and this covariance. Covariance is a scale version of the identity. For my p theta, for my denominator, again, I have another Gaussian distribution with the mean. What is p theta xt minus 1 and xt? P theta xt minus 1 and xt. It's another Gaussian distribution with a mean of xt and some covariance. And I'm looking at the KL divergence between two Gaussian distributions whose covariance is a scale version of the identity. So that formula is actually quite simple. So what it turns out to be, if I just look at one term here, one of the terms here, I call it, let's say, LT, the term, the loss function at time t. I'm going to get expectation over Q x0, 1 minus 2 sigma t squared, the difference between mu t, between the means xt and x0, and the mean of my other distribution minus mu t, xt, and t squared, plus some constants. Okay. So basically, I simplified this minimization to a minimization. Oh, I'm sorry, we are running a bit behind. So to this minimization. So I have my mean network, mu t, mu sub theta, xt and t. This is the network that I want to train as my denoiser. And here is the mean of this random variable, qxt minus 1 given xt and x0. Right? So this random variable is a function of xt and x0. Right? That's why in the mean here, you have both xt and x0, but here you only have xt. Basically, you want to match the mean of your denoiser to this quantity that is a function of xt and x0. Let me first recap what we have covered so far in terms of the underlying objective of diffusion models, the optimization formulation, and how we are going to try to deal with it. Okay, so let's do a quick review up until this point. All right, so as I mentioned, we have some clean samples represented by Q0 of X or QX0. And in the forward process, we add noise up until a point that we basically get a normal distribution. And in the backward process, we try to denoise it. In the reverse process, our goal is to denoise it one step at a time. So the model that we considered, the probability distribution of xt minus 1 given xt was a normal distribution where the means are, the mean of this distribution is a function parameterized by theta as a function of xt and time. And so far, we are assuming the variance is fixed, scaled version of identity covariance. And the whole idea is to learn theta, a set of parameters for my model, because in that case, I can start by sampling from a normal distribution as my p theta of xt. Again, this will be a normal distribution. And then I can go back one step at a time until the point that I reach to time 0, and I generate some realistic samples. Okay, so last time we discussed that likelihood computation is challenging with this particular probability model. Therefore, we used a lower bound, a variational lower bound on the log likelihood function. In particular, the lower bound that we computed was in this form. Log of the probability of x0 was greater or equal to the expectation of log of p theta x0 to t divided by q x1 to t given x0. And this expectation is taken, I'm assuming here x0 is fixed. Therefore, this is expectation over x1 to t given x0. And if you want to compute your average log likelihood, you are going to take another expectation over your Q0, the samples that you have, and you're going to take the average of the lower bound. So this is the elbow evidence lower bound or the variational lower bound that we computed last time. Elbow bound. Right, so the optimization objective then simply to maximize this lower bound. And since we want to have it in the form of a loss function, we are going to add a negative sign and minimize the negative of this lower bound. So what we reached to was minimization over theta, the negative of this bound. Expectation over Q minus log of P theta, x0 to T, Q x1 to T, given x0. That's basically the objective that we have. Okay, so last time there were like a couple of questions which I felt that it wasn't answered comprehensively. So one question was that, okay, so why do we need to do all of this? Here Q is a distribution. Given your Qx0, the other conditional distributions are Gaussian distributions. Why do we need to do this? Again, it is very similar in spirit to the approach that we did for the variational autoencoder. So Q is like a helper distribution for us. Without it, it would be very difficult to solve this optimization problem. So that's basically one point that I wanted to make. Okay. So the second point that I wanted to re-clarify was about this term, Q x1 to T given x0. Here, basically, you have x0, and then given x0, your conditional distribution of x1 given x0 is a Gaussian distribution. Same for other conditional distributions. So I can break this down as the following. So I can write this as Q x1 given x0. So this is a Gaussian distribution. Q x2 given x1 and x0 up until Q xt given xt minus 1 and x0. And there was a comment saying that, okay, look, you argued that Q has a Markovian property, meaning that if I have the distribution at time t minus 1, I have the distribution at time t for Q. Q is the forward this process, right? So if I have distribution at t minus 1 for Q, I have the distribution at time t. Then why do you keep x0 in your conditioning? Because when you have Markovian property, all the information relates to x2 is summarized in x0. Therefore, you can just drop x0 here. It's a Markovian property, right? Same here. You can drop x0 in all of these terms. Why do you keep it? All right, so let's say we don't keep it. If we don't keep it, this term, let's just focus on this particular term. Qx2 given x1, right? I need to compute this. Right? And in order to compute this, I'll have to write a Bayes rule. If I write the Bayes rule, okay, so why do I need to write the Bayes rule? If you again recall, P theta was the reverse process. Right? So you're going back in time. And we wanted to match them, the forward process and the backward process. So I need to write the Bayes rule in order to flip the indices. So if I flip the indices for this one, so I'm going to get Qx1 given x2 times Qx2 divided by Qx1. The problem is that I don't have these marginal distributions. I know the conditional distribution of x2 given x0, but I don't have the marginal distribution of x2. So the trick is that this quantity is exactly the same as this quantity, qx2 given x1 and x0 because of the Markovian property. I'm just like adding this x0 as a dummy variable in my conditioning. But when I do that and I write the Bayes rule, what do I get? I get q x1 given x2 and x0, q x2 given x0 divided by q x1 given x0. Do I have q x1 given x0? Yes. Do I have q x2 given x0? Yes. And we turn this into the other direction by knowing these variables. And do we have q x1 given x2 and x0? We argue that yes, we can in fact compute that. Okay. All right, so that's basically the trick, I would say, that is used in order to make the computation possible. Okay. So that was something that was missing from the previous argument that I made. So the whole argument then becomes we write the Bayes rule here, make the Q to go backwards, basically the reverse, and try to match the two distribution. So the final optimization that we get is something like this, right? So we get a term, obviously expectation over the Q. One term is minus log p theta of x0 given x1, that's the first term, plus a bunch of KL terms, say t greater than 1, KL term between two distributions, q xt minus 1 and xt x0, condition on x10 x0 versus p sub theta xt minus 1 condition on xt. So right, so that's it. This is the optimization we want to solve. So we want to minimize this over theta. That's the objective of our diffusion process. If you couldn't follow what I did so far, high level, we wrote the log likelihood. We couldn't solve it. We did compute a lower bound, a variational lower bound, again by massaging the log likelihood. And we reached to a term like this, but we have two distributions, one going forward, Q, the other one going backward, P. In order to have them matching, so we had to write a Bayes rule. So we did write the Bayes rule on the Q distribution. Now we have basically two matching distributions, right? So you have xt, and you are predicting xt minus 1, the distribution of xt minus 1 via your network, P sub t. And here again, you have xt, you are predicting xt minus 1 via your distribution Q. Yeah. But we highlighted that there is an additional x0 in the conditioning. You are not just in the Q, you are not just doing the denoising blindly from xt to xt minus 1. You assume that you know what is your clean image. So you are denoising in the direction of the clean image. That is really, really important. Okay, anyway, so we have this objective function. The rest is just optimization, how to solve, how to massage this objective function to turn it into a loss that is more manageable for us. And in fact, you'll see the loss function will be extremely simple. It's basically one line of the code at the end of the day for the implementation. Okay. So let's discuss each term separately. So I'm going to call this the first term, loss L0. And for each of these terms, I think I'm forgetting the summation here. T greater than 1. For each of these terms, I'm going to call them loss at t minus 1 because we are trying to predict the distribution at t minus 1, right? So that's the notation that we have. Okay, so let's first look at loss at 0. So do we have a formula for P of x0 given x1? Yes or no? Yes, what is that formula? Exactly, right? That's our modeling. Again, P is easy to go backward. You know, the reverse, I know how to go back. That's my modeling. So if you give me this xt, I know what is the distribution of xt minus 1, which is a Gaussian. So for loss L0, then P theta x0 given x1 is nothing but just a Gaussian distribution with a mean of x1 and my time is 1 and some variance. Okay, last time I mentioned at the end of the day, x0 is your image and image pixels are discrete values for each channel, meaning each, for example, color, the values are between 0 to 255. There are some implementation details how to map your output Gaussian distribution to such discrete values. So one implementation is to scale it, the numbers to be between -1 and 1, and then discretize this Gaussian. So your numbers are between -1, and then you have 256 bins. And depending on the value that you get, you predict the number in that particular bin, and that's your pixel value. And for the generation, you don't add noise at the end of the day. So these are like some of these technical implementation details in most standard diffusion modes. L0, easy to handle, we know how to do it. What about one of the other loss functions? Let's say LT minus 1. So let's focus on that loss function. So it's the expectation over Q, KL, distance between what? Q xt minus 1 given xt and x0 and P of xt minus 1 given xt. All right. Side note, I just want to make sure who is awake, who is asleep. What is this Q here? What is the expectation over? Q is basically the randomness, either in my input data or in my forward process. Like that's Q, right? So where are the randomness coming from? One is x0. If your x0 is fixed, suppose I'm doing it for one sample, then there's no randomness there. And then xt. Right? So if my x0 is fixed, let's say I'm doing it just for one example, and I'm going to take the average over all examples, this q will be basically nothing but qxt given x0. But when I'm writing q, I'm not carrying this notation, but I wanna make sure that you understand what q means. Okay. All right. So let's see if we can compute this KL. What is this term? Let's start with this term. P theta xt minus 1 xt. Do we have an understanding of this term? Yeah, right. So that's basically the modeling that we have. You know, I'm assuming you guys are a little bit shy and that's why you are not responding. So here, it's just a Gaussian distribution with a mean mu theta xt and t and some fixed covariance in this case. It's a Gaussian distribution, parameterized by this theta as its mean. What about this guy? Q xt minus 1 xt given xt and x0. So last time we argued, you can write this also as another Gaussian distribution. Write the Bayes rule, each term is a Gaussian distribution. Then algebraically multiply the densities, massage it. At the end of the day, you also get a Gaussian distribution. Okay. So I'm not going to do it. So at the end of the day, you get a Gaussian distribution for this term too. And I'm going to call the mean of this Gaussian distribution mu tilde of t, xt and x0. So that's the argument for the input with a parameter beta hat of t identity times identity. That's the parameters of this other Gaussian distribution. And last time we had a formula for the mean according to this particular equation. Mu hat was equal to 1 minus beta t xt minus beta t over square root of 1 minus alpha t bar times epsilon, where epsilon is defined as the following. xt, I know I can write it as alpha t bar times x0 plus 1 minus alpha t bar times epsilon. Okay, so this is the equation that we had last time. So this guy, again, basically what I'm saying is that this is a Gaussian distribution. It's conditioned on xt and x0. It means that the parameters of this Gaussian distribution will be a function of xt and x0. That's why in the mean, the input is xt and x0. It's a function of xt and x0. And this function, what is the form of this function? In fact, it is just a linear function of xt and x0. It is linear in xt, and it is linear in x0. Alternatively, since I know xt and x0 are related to each other via this formula, I replace that dependence on x0 as a dependence on the epsilon, the noise added to x0 to get the xt. It's an alternative formulation. So that's basically the formula for my mean. Questions? Okay, if not, I can continue. Then I have two Gaussian distributions with some mean vectors and basically scaled identity covariances, and I want to compute their KL. It is very simple. It is just the L2 distance, roughly speaking, the L2 distance between the mean vectors. So therefore, this whole optimization boils down to the following. Expectation over 1 over 2 sigma t squared. The difference between the means. The first mean, which is this guy, mu hat of t. Again, it's a function of xt and x0 because this distribution is a conditioned on xt and x0 minus the mean of the other distribution, which is simply mu theta of xt in my modeling squared. That's it. Okay, how can I use it for training? do I have a value for this vector, for mu hat of t? There is no theta there, so it's a fixed vector based on like samples that you're drawing. It's a fixed vector. Can I compute this mu hat of t? I'll need a volunteer, maybe you, because you asked some good questions last lecture. How can I compute it?
Know the data. I mean, you have the data for the X naught. You just add the noise in the sample, all the X from 0 to t, and then just use the compute.
Fantastic, right? So let's say I'm looking at a particular image, x0. So I have x0. I'm just going to draw like some Gaussian noise from my epsilon. Epsilon is according to Gaussian noise. And based on that, I have xt. Right? This is the formula for the forward process. Right? And I'll use this formula, xt minus beta t, it's a fixed parameter. Alpha t bars, they're fixed parameters of my forward process. I have epsilon, the same size of my image. Then I have this vector. It's a fixed vector. Again, I got a sample from this. Based on like the sample that I'm getting for my epsilon, I can do it many more times. But let's say I did it once, I get this sample. Okay. What about the other vector? So again, I have xt already. For my computation of this vector, I computed xt. Right? So that's the vector xt that I have. And obviously, I have t. However, I want to include in my input. That's fine. Then mu theta will be just a network to map your xt to another vector, the same dimension. Right? So the input and output, they are the same dimension for mu theta. And then you are comparing these two vectors. You are trying to align them, minimize the quadratic loss. That's it. So look at one example, x0. Again, let me repeat this. Draw a sample epsilon, then get a noisy version at a particular time. You can even pick your time uniformly, randomly between 0 to t. And get this vector. So then this will be a fixed vector for that particular realization. And then train your mu theta network to map xt and t to a vector that is aligned to the vector that you computed, to this vector. It's a quadratic loss function. And repeat it maybe like 100 times, 1,000 times. Hopefully this network, mu theta, will learn to denoise your input just a little bit based on the objective that we have. Make sense? Questions? No questions? Is this clear? Good. You feel happy? Okay. All right. So even though it is pretty much easy and computable and optimizable, I'm going to massage it further, just to like, because, okay, look at this. Like, so I get, for x0, I draw like a random noise, I get xt, then I compute this. It is basically a linear function. And then I train another network. I already have xt to map it to a vector and align them. Maybe I can even further simplify this whole process. You know, even at this point, I'm good. I can optimize this. I can learn my theta. The rest is basically some cosmetic steps just to make the whole process of training a little bit simpler. Okay. All right. Okay. So in order to make some cosmetic changes, let's look at the form that I have for this function. As I mentioned, it's a linear function of xt and x0, or alternatively xt and epsilon. It's equivalent. So what is the form of that function? It is in this form, 1 minus beta t, some constant, really doesn't matter, xt minus beta t divided by 1 minus alpha t bar epsilon. That's basically the form. But what about like the mu theta? Mu theta is a network. Right? So it's a network that takes an input as xt and t and outputs another vector. But I can maybe reformulate or recharacterize mu theta. Maybe instead of writing mu theta the way that I'm writing here, I can write it in a format that looks like something like this. So maybe I can define my mu theta as the following, because the design choice is in my hand, as 1 minus beta square root of 1 over square root of 1 minus beta t xt minus beta t over 1 minus alpha t bar times epsilon theta of xt and t. Mu theta of xt and t. So I'm defining my mu theta. Mu theta is my design choice, right? Maybe saying that it is just a neural network, I'm going to say it is in this particular form. There's a neural network here, but I'm going to multiply this neural network with a magic constant. It's my choice, and I'm going to subtract it from xt. Again, xt is a constant, and I'm going to multiply the whole thing with like another magic constant. Doesn't really change even like the complexity of your neural network. Right? So you had you have another neural network. You are doing a linear transformation of it with like some magic constants here and there. But like, how did I pick these constants? Like, why 1 over square root of 1 minus beta? Do you have any clue? So why this particular constant? Why not? Why not like another constant here? Yes. Because I want to like have it look like something like this, right? That's the whole purpose, just to, it's a cosmetic change. I'm just trying to have my mu theta to look like, at least in form, to mu tilde of theta. But that's basically it. So if I do this and I plug this in my objective, so what do I get? I get expectation over Q, 1 over 2 sigma t squared. That's what I have. Okay, so, and now I'm going to write, instead of mu tilde of theta, this term, and for the other one, I'm going to write this term. But I can factor out these terms, right? So I'm going to have square root of 1 minus beta t times xt. Let me actually open this up so it will be a little bit clearer what I mean. 1 minus beta t over this term multiplied by this term times epsilon. So this guy is nothing but my mu hat of t minus my mu theta, which is what? So that's the first term, minus times minus plus times beta t divided by 1 minus alpha t bar times epsilon theta xt and t. And these terms are basically mu theta minus mu theta. I just like rewrote, massaged it a little bit, you know, cosmetic changes. But as you can see, this term and this term cancels out. Right? 1 over square root of 1 minus beta times xt, and this is the negative of it. These two cancels out, and the coefficient here is the same between the two other terms. So I can just factor out the coefficient and bring it outside of the norm. So the whole objective can be written then as the following: expectation over q. I have this term already, 1 over 2 sigma t squared. And I'll just factor out this constant. I'll bring it outside of the norm. So I have the norm here. There will be like the quadratic form of it. What do I get? I will get beta t squared 1 minus beta t times 1 minus alpha t bar, the square root of this, times what? Epsilon minus epsilon theta xt and t squared. Right? And everything here is a constant. I assume my betas are constant, therefore my alphas are constant, and I assume my sigma is constant. Let's give it a name. It's a constant. I can compute this. Let's call it lambda t. It's a constant. For every t, I have a value for lambda t. Therefore, my optimization is just the following: expectation over q, lambda t, epsilon minus epsilon sub theta xt and t squared. And I'm minimizing over theta. That is it. That is the whole objective for training state-of-the-art diffusion models. How you do it? You get a sample, epsilon, usually from a normal distribution. And then you also pick a uniform t from, let's say, 0 to your capital T. So you draw a sample, so you have this. You pick a t uniformly, so you have t here. You can compute xt, right? Because for a particular x0, you just like do the forward process according to the distribution q. You get basically q xt given x0. You add noise to x0 to get xt, so you have a noisy version. And you solve this optimization. You learn theta, that is your parameter vector for your reverse process. And if you learn theta, then you learn basically p sub theta of xt minus 1 given xt, right? Remember, it's a Gaussian distribution parameterized by mu theta of xt and some fixed variance. Like if you learn theta, you have the mu function. Okay, you don't exactly get the mu function, you get the epsilon theta function, but mu is just the linear transformation of your epsilon function. Like some notational changes. You draw samples, you train it, you find the theta, that's it. You find the theta, you have your piece of theta, the reverse process. You can start from the end, basically Gaussian distribution now. Then you can go one step at a time, denoise it, denoise it, denoise it a little bit, and then you get your original sample, some clean samples. That is it. As you saw, like we started with like, this whole technical lower bound and the log likelihood function, so on and so forth. But at the end of the day, we reach to a pretty simple objective. So the only thing that is coming from all of those computations is this constant, right? Based on like the betas, we have like a very good way of computing this constant that can have different, basically weights for different times. And it is justifiable because this is a particular form that comes from the variational lower bound. So you pick like a set of betas, therefore you have the alphas, and then for a sigma, then you have lambda t for every t. It basically has different weightings for different times, principally combining the reconstruction error. But it turns out if you just pick one for all t during your training, it works better. It's a surprised face emoji. So what? Like we did all this computation. At the end of the day, we are just going to just drop this constant that was coming from our computation. And effectively, we are doing a reconstruction loss. So we are saying that, okay, just train a network to denoise your input a little bit. During training, in the inference time, still you do the process the way that it is intended to do. After you get the theta, you find the mu sub theta. Again, you add a little bit of Gaussian noise to it. And that is the denoise version, the distribution of it, a little bit of a denoise version of your input. So this is empirical evidence. So bottom line is, at the end of the day, in the training phase, just solve this optimization. You take a sample, noise sample, you pick one of your training examples from QX0, you pick a time uniform between 0 to t, and train a network to minimize this objective. That's the optimization for the training. And in the inference time, after you trained, you learn this theta star. In the inference time, So you have theta star, right? You basically have mu theta star of xt and t. So you generate a sample. If you want to go from time t-1 to time t, you can use this distribution p theta xt-1 xt according to a Gaussian distribution with this particular mean fixed covariance. You generate a sample from for the time before and you move forward. This is called DDPM. Okay, so it stands for denoising diffusion probability model. Denoising diffusion probability model, DDPM. Okay, so with this spirit, that's basically the foundation, right? That's one way of doing it. Based on this work, there have been like many variations, many different ways of doing it. Because as you saw, okay, it has some grounding on some theory, right? So you're saying, okay, maybe started log likelihood, we did a lower bound, so we don't know how tight that lower bound is. And then we did like some dropping of some of these constants, so on and so forth. So it was maybe half supported by some of these foundations, and some of them are based on heuristics. And there are like some other follow-up works building on this to explore other variations of diffusion model. But still DDPM remains perhaps maybe the state of the art in many of the many of the image generation models, or very close to the state of the art. Okay. Just one last note is that you can, I mentioned all of the beta thetas and all of these others. These are called scheduling. We assume they are constants. You can also optimize them. It may improve your generation a little bit. Nothing really fundamental. All right. That is all I had for the DDPM part. Let me pause and see if there are any questions before I move on to other related topic with respect to diffusion models.